Hi students, welcome back to the online video lectures of the medical imaging course. This is the third video lecture on understanding the physics of MR imaging. The outline of this video lecture would be, first we would be discussing about the precession of this magnetic field, how it rotates around suppose we are applying B naught in the Z direction, how it rotates around the Z axis. Then we would discuss about interaction of this magnetic field when you additionally apply a B1 magnetic field at radio frequency, and then you would see there that this would result in magnetic field in the longitudinal direction as well as in the transverse direction. And then how once you withdraw your RF field, magnetic field, how is this going to impact the magnetic field that you are obtaining. And finally we would be deriving empirically the Bloch equation that assimilates or summarizes the discussion so far. Okay, let's start. Let me first recap few important concepts that we discussed regarding applying the magnetic field B naught, the strong external magnetic field. For this purpose, you consider a sample or a voxel that you would like to image. Then if you are not applying any external magnetic field and assuming that it has a lot of hydrogen atoms in it, which is having in turn one neutron in its nucleus, and this has a property of spinning, right, and resulting in an angular momentum, and this angular momentum is giving you magnetic properties. So it acts, each atom of hydrogen would act like a tiny magnet, but it's orienting in its own orientation or in its own direction, as you could see here in the first image. Then what if you are applying a magnetic field, right, let's say in the Z direction, and then the alignments will no more be random, and we discussed it in very detail in the last lecture as well as the lecture before that, that this would get oriented either parallel or anti-parallel to the applied magnetic field. All these magnetic dipoles will orient either parallel or anti-parallel to this magnetic field, with slightly more preference towards aligning parallel to it. And then this is how the middle image is that showing you. Then if you just cancel out the number of dipoles that are there parallel to with anti-parallel, all you would left with would give you a magnetization. For that particular sample or a voxel, let's say, is of the size of millimeters, right? And then we also had studied how much magnetic field it could give you. For example, under 1 Tesla and room temperature, let's say if you have 2 million spins, out of them 7 more will be aligning themselves in the direction of applied magnetic field B naught, and thus this resulting in giving you a magnetic field vector m bar. Okay, the resulting magnetic field vector, let's call it m bar. Then what would happen? This is in the direction of B naught. Now then we also have seen from quantum physics point of view, where we are dealing with the angular momentum of each of the spins, that there are two energy levels. The one which is in parallel is that one with a low energy level, and the other having an energy high energy level. And we also calculated the amount of energy that would be required to make a transition from this low energy level to the high energy state, right? And then we discussed the same thing about this at a macroscopic level, about this capital M bar, how does it going to behave, this M bar. And we arrived at the expression dm bar by dt is equal to gamma times the cross product of m bar t, okay, the magnetic resulting magnetic field, and the applied external magnetic field b bar of t. So as we discussed in the previous lectures, this m is a function of x, y, z as well as time, right? That's what we discussed. So then we derived this equation of dm bar by dt equals to gamma times the cross product of m bar t with b bar t, and this is the rate of change of angular momentum is giving you torque. That's how we derived this equation in the last class. And I would like to add few more points here. Now suppose this is actually oriented in the z direction, just resonating at z at the frequency, resonant frequency of gamma times b bar. Now what would happen if I apply now additional field which I would call with the name B1. If I am applying a field in the xy plane B1 at the resonant frequency, if I am going to apply a magnetic field in the with this, such that this vector m bar, because of that, so imagine a top which you made it rotate, is rotating there, and if you poke it, okay, then what would happen? If you just poke it and leave it, the axis with which, the angle at which it rotates with respect to its z axis is going to vary. In similar lines, what would happen is something which is just resonating at the z, and now in addition to this force of b naught, if you are applying radio frequency, at a radio frequency you are applying b1, a small value compared to the b naught, then it would be rotating at a particular angle around this z axis. This would be rotating with symmetrically around this z axis, okay, and this is referred to as precession. And well, you could also compute here at what rate it rotates, or at what frequency it rotates. So for that, just take a closer look at this expression of dm bar by dt being gamma times the cross product. Now if you would like to know, consider a case where you tipped it to fall on the xy plane, and this rotating on the xy plane, okay. So this you applied in the xy plane a force such that it has tipped to the xy plane, and then you stopped your excitation and it's rotating in the xy plane. So then this is the top view of it I am plotting now. Instead of now looking at the all these vectors in the 3D plane, I would comfortably move to xy plane, okay, and then try to make an interpretation of this equation. You could see here your m bar is now on the xy plane. Consider for a moment, without loss of generality, that it is here, let's say on the x axis here, and now it as you know, the torque applied would make this object to rotate. That's a well-known phenomenon. And now what we would like to see is at what frequency is this going to rotate. Now how do you know that? Say this is an m bar, vector of magnitude, magnitude of that vector m bar would give you the length, and now this is going to rotate. Now that means for making one rotation, if it is making, right, then its circumference is 2 pi times the magnitude of m, and from here you know the rate at which it is rotating, which is dm bar by dt is this value. Now what you would like to compute here is how much time does it take to complete one rotation. So it's of length m bar here, right? It's going to rotate over a period, over a length of 2 pi m. That's the circumference, because it's rotating there with the same length they're assuming that. And then what else do you know? The rate at which it is rotating, dm bar by dt, you know it. So per second, let's say this is what it is rotating. So it's a simple proportionality. If you look at it, for example, in 1 second, okay, dm bar by dt, take the magnitude of it, so that's equal into gamma times the magnitude of this and magnitude of b bar vector. So that's what it takes in 1 second. So for rotating 2 pi m bar, how much time? If you take it, it's a simple, well-known, straightforward thing to work out, and you will know that the time it takes for making one complete rotation is 2 pi over gamma times pr. Now suppose if you want to compute the frequency at which it is rotating, this is equal to 1 by t, that's nothing but gamma over 2 pi times the magnitude of b bar, right? This is not something, the equation is not something we are come across here for the first time. It's the same thing, frequency, even when you are making computation of how a dipole would be moving, okay, around its axis, is the same frequency that you have there. So This is telling you, again, the summary of this is, if you are applying a magnetic field in the xy direction, then m bar, this is what we refer to as Larmor's frequency in our previous classes while doing analysis using quantum physics, and a single dipole, magnetic dipole with the same frequency, even your m bar at macroscopic level, which is accumulation of all your individual magnetic dipole magnetizations, that also would be rotating at the same frequency, given by gamma by 2 pi times the magnitude of the b bar which you have applied there. Right now you would be applying this b bar in such a way that, of course, it would be able to tip from the original one to the xy plane. Right now you stop the excitation. Now you see what is happening here. Again, I moved here to the xyz representation, but you could equally make it draw it in xy as well. So there is a rotating magnetic field here. M bar is a magnetic field. It's a rotating magnetic field is there. And now from the Faraday's laws, you know that if you keep a coil there, it generates a voltage in that coil. So this coil is, you keep it in the xy plane, and this is the same coil that you have used earlier for transmitting the B naught. Then you stop transmitting, and this you use it as receiver. Why we call it as RF coil? That discussion again, connect this to what we discussed in the previous class, this gamma by 2 pi into the magnitude of B bar. This would eventually be equivalent to this B1 magnitude that you are applying in the XY plane is negligible compared to the magnetic field that is there in the Z direction, which is of the order of 1.5 Tesla, 3 Tesla, 7 Tesla, and so on. So compared to that, this is small. So this would turn out, if you consider the hydrogen atoms, this is in terms of the in the range of radio frequencies. That's why what you are transmitting is an RF pulse, and what you are receiving is also an RF pulse there. Hope that part is clear. Now we are going to take a look at what would happen once you are applying this 90 degrees excitation field and bring your m of xy into the xy plane, and then you withdraw your signal b1 of xy that you are applying in the xy plane. Only now there is this external high magnetic field that you are applying in the z direction. So you could think of it as there is a force that is trying to pull it up because it's in the z direction. Now what is of our interest now is to study what would be the contributions of this m in the xy plane, projection of this m bar vector on the xy plane. How is it going to change? That is one thing. And the second thing of our interest is how is the projection of this m bar vector on the z-axis, along the z-axis, is going to vary. By the way, when you are applying it in the z direction, your magnetic field, this xy plane, you refer to it as transverse plane. So you would be referring the xy plane as transverse plane and the z-axis as the longitudinal axis. So what is of our interest now is to study how the magnetic field would vary in the xy plane. That means how m subscript xy, if you are going to call it, okay, how is that going to vary over time after you withdraw your RF magnetic field, RF signal. And the second one is how is your mz is going to vary, that is the projection of this m bar on the z axis. Okay, so as you could rightly guess here, if you think about it, is that since there is no force that is applied in the xy plane, obviously this would eventually would come out into the z direction. This m bar would again come to restore, it gets restored back into its original position, which is in alignment with the applied magnetic field. So we will just have an intuition here rather than having a very rigorous proof here. So this you could call it as, you assume the magnitude of this vector as m naught. So finally, after a sufficiently long time, this would again come back to m naught, and the way it recovers is going to happen exponentially. So you could say that mz equal to m naught into 1 minus e to the power of minus t over t1. So this t1 is telling you at what rate it is going to come back. These are equations, if you can compare with the charge across the capacitors, voltage across the capacitors, or the current across the inductors, what would happen there? You would see a very similar behavior here. So once you withdraw, to repeat, your field along in the xy plane, this would again come back to its original position. As you could see here, at t, for large values of t, okay, what would happen? This term is going to become 0. Again, the rate at which this is going to become negligible is dependent on this constant, and then this is equal, then it would be, when this is 0, this would be equal to m naught for a sufficient, after a sufficiently long time duration. Okay, and then, by the way, this longitude, this is called as relaxation, because till then you applied a force and now you withdraw it, so you relaxed it from the magnetic force that you, magnetic field that you have applied in the xy plane. So these are called as relaxation. So it would come back to its natural state now. Now, this is also referred to as spin lattice interaction. The reason being, now it's more like you could again correlate it with the quantum physics concepts that we have discussed in our earlier classes, where it tries to again establish a thermal equilibrium by shedding off the high energy values and bringing it back to the normal state that was there before you do any before you have applied any magnetic field in the xy plane. So how fast it would come to its original m naught value in the z direction would essentially be depending on one side, the external magnetic field, the amount of external magnetic field you have applied. That's one thing. The second thing, it also depends on the proton density that you have in your sample that you are studying, or the tissues that have within the oxel that is currently under evaluation, right? These are the things that would have a call on how much time is it going to take to come back to its state. So this longitudinal relaxation is also referred to as spin lattice interaction, and this T1 for this reason is also referred to as spin lattice time constant. Okay, and now let's take a look at what is going to happen in the xy plane. Just the moment after you withdraw your magnetic field in the xy plane, by the time what we are considering is it is in the xy plane. So that's the time when you have this whole m naught vector is in the xy plane. So that time you have an m naught value, then it is coming back here, okay, to the z plane. So over the time, its projection on the xy plane is going to be 0, and that's why you have here m naught into e to the power of minus t over t2. Notice here the time it takes for the longitudinal relaxation, in other words, for it to come back to m naught, is going to be different from the time it takes for the transverse relaxation. In other words, the magnitude in the xy plane of this magnetic field to become 0. The reasons are twofold. First reason, that earlier you have seen that there is a spin lattice interactions that are going to happen. Because of that, as it is coming up towards the z plane, anyway the xy component keeps reducing. In addition to that, another phenomena that contributes to the mxy, that is magnetic field in the xy plane, to become 0 is spin-spin interactions. You could think of it in this manner. Again, you now come back to the quantum physics, where each dipole is rotating at its own in its own axis, right? Now all of them are rotating now either parallel or anti-parallel. That has happened now. But in addition to that, what could happen is the phase could be the starting points, although they are either in parallel or anti-parallel state. The starting points for each of those spins, despite the same alignments, could be different. Because of that, now although everything is in this direction, let's say each dipole, if you take the projections of its on the xy plane, then each even before that becomes zero, because of anyway once it comes in alignment with the z-axis, the magnetic vector m bar coming in alignment with the z-axis would anyway make it zero. But even before that, as each dipole is rotating in its own with its own phase, now orientation is same but with its own phase, what's going to happen is once you take the projections of it on the xy plane, they are going to cancel out each other well before even this completely comes magnetic field vector comes completely in alignment with the z-axis. So this is called as dephasing. Because of that effect, the relaxation that happens in the transverse plane is much faster, and this is referred to this T2 constant, and that's what would dictate the number of spins and number of other factors is going to dictate it, the what would be the value of this T2. So that's why T2 is referred to as spin time constant, and this is going to decay once you are freeing it from applying any magnetic field in the xy plane. So this is also referred to as free induction decay. And spin although the effect of spin lattice interactions are there, okay, that are bringing them into a low energy state and making it align, making that into more into the z direction, the spin interactions are also there, or in other words the dephasing of the magnetic fields of these dipoles is something that makes the magnetic field in the xy plane decay faster than regaining of magnetic field in the z direction. So that's why it is written as mxy equal to m naught times exponential of minus t over t2. Okay, now you could for example, again let's come back here. Given this equation, that's the magnetic field, okay, magnetic moment, rate of change of the magnetic moment, again dmz by dt you could compute, and that would be equal to, in the z direction, if your rate of change of this magnetic field vector if you are looking at, that would be minus 1 by t1 multiplied with mz minus m naught. Now similarly here we are going to do it for the magnetic field come in the xy plane, the projection of it in the xy plane. For now we are not because of the way it simplifies the math, we are looking at in the xy plane rather than making its projections on individually for x-axis and y-axis, okay, unlike the one we did earlier mz there. But here for the time being we are restricting ourselves to its projection on simply on the xy plane. So again you take a derivative of it, so that would give you dmxy by dt equal to minus m subscript xy by t2, right? So this would be in the order of milliseconds, and on the other hand t1 is much larger, so for it to relax and regain would take order of seconds, where this usually takes in the order of milliseconds, right? So if you want to take a look at how this would be there, as I mentioned, if you look at the T1 depends on spin lattice interactions as well as the magnetic field strength that you are going to apply. So here on the x-axis you have magnetic field strength B naught that you are applying in Tesla, and here are different tissues, let's say fat, liver, kidney, white matter, muscle, gray matter. So this would tell you that for a given for an applied magnetic field, how much time it takes for longitudinal relaxation or T1 relaxation. So you could see here, let's say 1 Tesla for example, this could take around so as you are increasing the magnetic field, the amount of energy transactions that has to happen in terms of the magnitude of that energy is larger, so the relaxation time would keep on increasing. So you could make a similar interpretation about the proton densities of various tissues, and depending on that They would be, for example, the gray matter is something that takes a lot more time. So this is how you could in fact make a distinction and figure out what exact for a given magnetic field strength, depending on the magnitude that you are observing at a given time. Like for the Z's, for the MZ, you could figure out whether it's a gray matter, whether it's a muscle, white matter, kidney, liver, fat, and so on. Okay, and coming to the T2 relaxation time, that is for the MXY to die down. This you could notice here, it's hardly of the order of milliseconds, and this is in fact is not dependent on the magnetic field strength as such, because the dephasing phenomena makes it die down much faster than the complete the lattice spin lattice interactions happen. So that's the basic. So this is very much sensitive to the kind of material that you have, and it's much faster. So you could see here for gray matter, let's say this is 100 milliseconds, white matter 92 milliseconds, and let's say liver 43 milliseconds. So it's some order of milliseconds. Okay, so that's as far as the relaxation of the magnetic fields in the xy plane as well as the z axis are concerned. One last point is to empirically now come up with an expression for the rate of change of this magnetic moment, the macroscopic magnetic moment. So that equation is referred to as Bloch equation. So the first thing, when you are applying B naught alone, then you have seen this dm bar by dt equals to gamma times m bar t cross product of it with b bar of t. This we derived in the last class. Now we have empirically derived now dmz by dt, and here dmxy by dt, and then if you combine it, then you are going to empirically get what's the what is actually referred to as Bloch equation. So he's the one of the core Nobel laureate for figuring out this nuclear magnetic resonance phenomena, along with Purcell, who both of them independently did that. And this is one of the very fundamental, very important equation in magnetic resonance imaging. Now you could see dm bar by dt equal to m bar dot product of it with gamma times b bar minus this. Now what I'm going to write it is mxy. I'm writing it as mx times x bar plus my times y bar by t2 minus of mzy, this is in the z direction, minus 1 by t1 times mz minus or this is 1 over t1 mz minus m naught times z cap. So x cap, y cap, z cap are unit vectors in the x, y and z directions. Okay, so this is the important Bloch equation. That's all for now in our course as far as the physics of MR imaging is concerned. Now from the equation in the next class, what we are going to see is from the equation of dm bar by dt, how do you get the expression for m bar of t. Okay, and then we would continue with the imaging aspects of this magnetic resonance imaging. Okay, thanks for watching. See you in the next video lecture. Bye, take care.